Hello, we are Moscow Robophobes. Our project is dedicated to dangerous situations prediction when moving mobile robots using depth maps. Our team develops means to control robotic wheelchairs, including for people with severe upper limb impairments who cannot use a classic joystick. The eye tracking technology allows creating a system controlled by eye movements. You drive where you look. Such method of control can be quite flexible, allowing complex maneuvers. However, accidentally shifting the gaze to a visual distractor can be falsely recognized as a command, which can lead to a crash. This is where robotics comes into play. By equipping the wheelchair with a number of sensors, we can analyze the environment and evaluate the user's commands, blocking those that could be dangerous. So, we have data from sensors, as well as the current and desired speed for the next time periods. And we want to get an assessment of the situation in which we will get while moving with the chosen speed. Since various conditions can be dangerous or undesirable in a realistic setting and the usual navigation algorithms only avoid direct collisions, a more general method is preferable. This problem can be approached in a data-driven way, by training the neural network model to make the required predictions. The training data can be obtained by physical simulation, forcing the model of the wheelchair to drive in different worlds. However, an important point is the preparation of such data so that it corresponds to the real input as much as possible. To do this, we use the methods of stereo depth generation from 2 images and 2 simulated cameras, instead of the built-in depth camera plugin in the Gazebo simulator. Trained models can also be tested in the simulator by controlling the wheelchair with the gamepad. The control algorithm blocks commands when the danger level exceeds a certain threshold. It can be seen that the model successfully identifies dangerous situations when moving towards them. We were also experimenting with different architectures to either predict dangerous situations in general or split them down into classes such as collisions and falls. To test the portability of the models trained in the simulation to real world, a small dataset was collected on a real wheelchair. The dataset was automatically marked using the existing safety system that is based on a laser range scanner. We are testing different ways to transfer models from simulation to reality, but right now the best performance is for a model trained purely on the real data. By controlling the wheelchair with a joystick, the capabilities of the trained models were tested. They recognized obstacles, but were noisy, sometimes causing frequent changes in prediction, causing jerking during movement. For a comfortable movement without jerking, it was necessary to add a low-pass filter to the output of the model. By adjusting the threshold parameters for predictions, you can control the distance at which the wheelchair stops when a dangerous situation is detected. We really like the OpenCV Lite camera, both for the quality of the depth map and the ease of connection and installation of the necessary software. After that, we tested the system using gaze control. The system successfully blocked attempts to crash into a wall while allowing movement in a free direction. We consider the prototype of the system to be quite successful, but there is still a number of problems that should be solved. With the arrival of dry weather, we will conduct full tests in an outdoor environment since this is the intended conditions for the system. Instead of estimating the danger of the situation, sometimes it would be more useful to predict the pose of the robot, also taking the environment into account. Due to the limited view angle of the camera, the system is not able to see all the dangers that, for example, can occur when reversing or turning in place. To improve that, the number of cameras attached to the wheelchair can be increased, as well as training the model to remember the environment configuration in a few past steps. Unfortunately, we did not have time to transfer the calculations to OpenCV, because our architecture requires a specially prepared depth map as input, but we hope to tackle this task during a more detailed study of it. In conclusion, we would like to thank the organizers for the opportunity to work with the new stereo camera depth hardware and participate in this interesting competition. We would also like to thank the ROS robotics community, machine learning, computer vision and other developers, whose software libraries helped us realize this project, as well as our robotics laboratory and institution,